Okay, let's do an example problem with the pendulum. Let's take this one that's about the moon. This is chapter 14, problem 30. And it tells us that the free fall acceleration on the moon, g on the moon, is 1.62 meters per second squared. It says, what is the length of a pendulum whose period on the moon matches the period of a 2-meter long pendulum on the Earth? So what is L for a pendulum on the moon whose period equals that of one on Earth that has L equals 2 meters? There's a couple of ways we can solve this problem. Let's do the sort of what I'll call the brute force technique first. So the period of a pendulum is 2 pi times the square root of L over G. And so on the Earth, we're told that the pendulum has L is 2 meters and G on the Earth is 9.8 meters per second squared. So that gives us T equals 2 pi times the square root of 2 divided by 9.8, a consistent set of units. So we just get our calculator out, and 2 times pi times the square root of 2 divided by 9.8 gives me 2.84 seconds. So the question says, how long a pendulum do we need on the moon in order to have the same period as that? So on the moon, we're going to have t equals 2.84 seconds, and we have g equals 1.62 meters per second squared, and the question is, what is L? So we use the same equation, t equals 2 pi square root of L over G, but now I've got a different value of G, and we're told T, and we have to figure out L. So remember, it's always, even though the temptation I know is perhaps irresistible to put numbers in early, wait until the last second to put numbers in. Wait until you've got L equals blah to put the numerical values in. It's always better to, easier and to avoid making mistakes if you keep things symbolic until that last step. So I want to get this equation turned around to be an equation for L equals something. All right, well, let me first just make it square root of L over G equals T over 2 pi. So what I did there was just divide both sides by 2 pi, and then I just swapped what was on either side of the equal sign. Now I've got to undo that square root. The way to undo the square root is I square both sides. That gives me L over G equals T over 2 pi squared. Then I can multiply both sides by G, and I get L equals G times T over 2 pi squared. Nice thing about that is now you've got that equation. You can use it for any planet or anything you want. Now we can go ahead and put our numbers in. We have 1.62 times 2.84 divided by 2 pi squared. And let's put that in the calculator. 1.62 times 2.84 divided by 2 pi, and all of that squared, and I get 0.33 meters. Now let's ask ourselves that we're not done until we ask ourselves if this makes sense. Remember that our equation for the period is proportional to the square root of the length. So that means a longer pendulum has a longer period, and that's consistent with our everyday experience. You can take something and hang it from a string, and if it's on a little tiny string, it's going to be going back and forth like that. And if it's on a really long string, it's going to be very sedate and gentle, like a grandfather clock pendulum. And so uh, on the moon, this is a shorter length, which would say a more rapid rotation. But of course, the gravitational pull is weaker. And so that gives us the uh, why we have to have a shorter pendulum. I said there were a couple of ways to do this problem. This is sort of the brute force way. We just put the numbers in and figure it out. The other way is just by saying, okay, in this equation I've got circled in blue up here, the period is proportional to the square root of the length over the acceleration due to gravity. So the acceleration due to gravity on the moon, 1.62 g on the moon over g on the Earth is 1.62 divided by 9.8, and that ratio is 0.165. It's about a sixth the gravity on the moon, about a sixth that of the gravity on the Earth. And the equation you can see here for the period has got L over G. So if G is 6 times smaller to have the same period, L must be 6 times smaller. Or more precisely, if G is 0.165 times the Earth value, L must also be 0.165 times the Earth value. So the length of the pendulum on the moon should be 0.165 times the length of the pendulum on the Earth. 0.165 times 2 is 0.33. So that's a more elegant way of doing it than the brute force way, but either way gets you the same answer.